Hi, this is Physics 2211, Lab 3, Black Hole and Orbits. Introduction. The purpose of this lab is to create the orbit of the star around a black hole by finding the mass of the black hole, and then to find the correct speed of a ship and planet. Some models and fundamental principles use our Newton's second law, parallel and perpendicular components of net force, gravitational force, free body diagrams. The preview to the main result, so mass of the black hole and initial spaceship velocity, as you can see. The main physics concepts are Newton's second law, parallel and perpendicular forces, and gravitational force. The first equation demonstrates the relationship between the net force and the rate of change of momentum. This was mostly utilized in part 1. Equations 2 and 3 show velocity and position update, which enables the motion and path of the code to be affected by the gravitational force. Equation 4 shows the force of gravity, which was the only force present in the code. The next equation shows the components of the net force. Parallel force changes velocity and perpendicular force changes direction. The last equation demonstrates how to solve for momentum. Why? All these physics concepts help to contribute to finding the mass of the black hole in the spaceship's orbit. The only force playing a role is gravity, but if it acts on everything, the orbit leads to both parallel and perpendicular forces, which means they are changing direction and velocity based on the force of gravity. Gravitational forces go in equal and opposite directions, and by utilizing the change of force and velocity and position update formulas, the simulation is able to demonstrate a path of these objects. The systems and surroundings and initial conditions. So for part 1, the systems, the star, the surroundings of the black hole, and the initial conditions give you the mass, the big G, and radius. And then for part 2, you have the system as the spaceship, surroundings as the planet and moon, and initial conditions are the planet mass, moon mass, ship mass, and big G. Procedure, so we calculate the mass of the black hole using the parallel and perpendicular forces first, and then this allows us to see the mass of the black hole because it affects the strength and force of the gravity that is causing the change of momentum. And then we found the necessary speed for the spaceship to orbit the planet and moon without crashing, and this uses gravitational force and the velocity and position update formulas to find the orbit, and it was slightly guess and check because it needs to be fast enough to not crash, but slow enough to stay in its orbit. So this is part 1 of the code. I inputted the momentum equation, the change of velocity, and change in momentum. This allows the code to have net force and the components. We then use the force of gravity to calculate the mass of the black hole, and we also change the arrows to demonstrate the directions of the forces like a free body diagram would. This image shows the output of the code, and the final calculation shows a mass of 7.3838 times 10 to the 33rd kilograms for the black hole based on my email input. This shows part 2 of the code. I changed my forces on both the ship and moon to reflect gravitational forces with the different masses and radiuses. We also use the position update and velocity update formulas to demonstrate the motion of the moon and ship. It was then guessed and checked with the ship's velocities to find the necessary speed of the orbit to not crash. This image was output of the code. The final speed I used was vector 14105,36821, 0 meters per second, and it's not a figure 8, but it is affected by both the moon and the planet. The outcome, so by finding the mass of the black hole, we are better able to analyze its gravitational effect on objects in space. By knowing the spaceship's speed, we are better able to know what the necessary velocity is to correctly orbit the moon and planet, which allows astronauts to perform their mission. It also helps us to better understand the gravitational effects of the planet and moon. Some similarities and differences. So since we collected no true data and only utilized the coding, there is nothing to truly compare within our code. Compared to the other people's codes, the numbers will slightly differ due to the many different velocities that will allow the spaceship to orbit, and the different emails in the first part would cause different black hole masses. The only criteria that it could not be faster than the speed of light, but it needs to be fast enough to stay in orbit. Both codes found very different things, which furthers our understanding of physics. The code differs from the figure 8 pattern due to a different initial velocity utilized. While the figure 8 pattern may be impossible, the path of the spaceship in my code demonstrates a similar effect of the gravitational forces. So possible sources of error, so rounding numbers and calculations, it would be better to use smaller delta t values in order to increase accuracy. Not making a figure 8 due to trial and error, so the approximation of the black hole mass, and guessing of initial velocity, so it could have had a cleaner orbit. The planet has a completely fixed location when in the real world it would most likely be moving slightly, and the assumption that no other forces other than gravity are actually on the planet. So for the additional questions, what does this mean? So the result demonstrates the gravitational effects on both the black hole, which is part 1, and then the sun and moon, part 2. The net force demonstrates the sum of all forces acting on the object, so the change in momentum is dependent on the speed and acceleration of the object. The parallel components affect the momentum, so changes based on direction of F net parallel, while the perpendicular components of force change the direction of the momentum. Rate of change of momentum and net force are mathematically the same because F net equals dp dt, and then dp dt is easier to physically observe due to its dependence on time, velocity, and mass, which are all easily observed. F net is harder to observe without the calculations necessary. And then to predict the motion of the entire system, you would need to include the planet's motion in the system, whereas we assumed it was stationary. If you're using the entire system from both parts of the code, it would be necessary to look at the planet, star, black hole, moon, and spaceship. They all have a slight effect on each other due to the gravitational interactions. Dominant interactions would be dependent on the radius and the mass. So the black hole is the highest mass, would have the highest interaction, followed by star and planet, and the spaceship would have the least effect because it has the smallest mass. Thank you.